Hello everyone, this is Vasanth, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss about built-up beams and shear flow. So why this topic is important? I think you had observed the beams which are made up of two or three pieces in real life. So how they connected these pieces? Generally, they connect these pieces by using the nails or screws. So if you observe that they will place that screws with some uniform spacing S, right? Some uniform spacing. So how much spacing they provided, that will depend on the loading. So to understand that, we need to know about the concept called shear flow. That will help us to find out the space between the nails. So let us see, this is one beam which is made up of this one. This is one piece and this is one piece. This is another piece and this is another piece. So these four pieces are connected over here, here, here. This is cross-sectional view, by the way. So you can connect these by a glue, or you can punch a nail, right? You can punch a nail like this. You can punch a nail like this. You can punch a nail like this, right? Or you can use screws, anything else, okay? So what are built-up beams? So built-up beams are fabricated from two or more pieces of material joined together to form a single beam. So they will act as a single beam. Okay. So this whole structure will act as a single beam. So this is made up of this I beam and these two rectangular beams, right? So these are connected. These are connected by bolts, right? See, if you see, these bolts are provided at a uniform spacing S. And if you see over here, this is also a I beam and this is known as plate girder. So if you see, this is made up of three pieces, this one and this one and this one. So these three pieces are connected by welding. Okay. If you see this one, this is made up of many small rectangular portions. So these are connected by a glue. Okay. And we can also use screws or nails. Okay. These are connected by nails. So these nails, glues, fasteners, etc. are required to resist this shear, okay, and prevent members from sliding against one another, right? So we already solved one problem in previous lecture. That is the case of this one only, right? So to find out this spacing S, we need to know about one concept that is known as shear flow. So what is shear flow? Shear flow is the horizontal shear force per unit distance along the longitudinal axis of the beam. So see, if this is a I beam, so suppose this is a rectangular beam, then this will be the longitudinal axis, right? So suppose in this region, the shear force, to take a part element, the shear force in it is F. Then F by this distance dx will give us the shear force per unit distance, that is known as shear flow. So let us derive the formula. So similar to that shear stress formula. So shear stress formula. So shear stress, similar to that, if you take a part equilibrium, then on this will be the forces acting, and these forces are resisted by this shear stress. So we can take as net force as shear force. So here there is no assumption of shear stress variation. Whatever may be the shear stress variation, the net force will be same, right? So we are not talking about the shear stress variation. So we are not assuming that the shear stress variation is constant across the width. Okay. So this is F3, right? So this we can write shear, this F3 will be is equals to integral m plus dm into y divided by I minus integral my divided by I, right? So this F3 will be is equals to integral dm y divided by I. So this F3 is total shear force in that cross section, right? So we can write F3 divided by dx. This is the length dx, right, along longitudinal axis. So this will be shear flow represented by Q or F. Okay, that will be is equals to dm divided by dx into 1 by I. Sorry, here it will be dA, right? So into dA. So integral y dA. This y dA will be the of this portion. So this will be given by, this is V divided by I and this is Q. So shear flow Q is given by VQ by I. And one more thing is that here we didn't assume that the shear stress variation across the thickness T is constant. That we are not assuming. That doesn't matter because in this discussion there is no matter involved of shear stress variation, right? So this formula is applicable for any cross section, okay, of prismatic beams. That you need to understand. But that shear formula VQ by IT, that will not give accurate results in the cross sections which look, suppose if you take a circular one, it will not give a correct shear stress variation at this point because here the shear stress variation will not be constant across this thickness, okay. So that assumption is not there here, okay. So this is about shear flow. So if you see, shear formula is VQ by IT and shear flow formula is Q is equals to VQ by I. Okay, right? So now how to calculate this shear flow? See, VQ by I. I is of whole cross section. V is shear force at the cross section. The only variation will be Q, that will depend on the point of consideration. So if you take this T beam, this T beam is made up of two materials, right? This is one and this is two. So these two are connected by using a nail, right? So to calculate the spacing of these bolts in longitudinal direction, how we need to calculate? See, so we to hold these together, this nail should resist the maximum shear stress in the beam, right? Similar to that glue wala problem we solved in previous lecture. So what Q you will consider? So you need to find out the shear flow in this plane. So in this plane you need to find out the shear flow, right? So for that plane, so this will be the Q cross section for Q. So for that we write Q will be is equals to VQ by I. And first we will go and find out the maximum shear force in the beam. So we will get Q max will be is equals to V max into Q divided by I, right? So this Q max, see, we will generally provide the uniform spacing, okay. So this bolt will resist the shear stress in this region. So see this, if this is S, so this will be S by 2 and this will be S by 2. So if in this region the shear flow is Q, then Q into this S will be the shear force resisted by the bolt, right? So that will be is equals to Q max. So sorry. So shear strength of the bolt should be at least Q max into S. So S should be Fs divided by Q max. Okay. This is the maximum spacing we can provide. See, if you increase the Q max, then the spacing will decrease, right? If you increase the Q, the spacing will decrease. So the S for maximum value will be minimum value, right? So the minimum spacing should be like this. We can, if we put less than that value, it will be more safer, right? So this is like that. Now let us go to this problem. So in this case, see here there is nail, and here also there is nail. So these two nails should resist. This nail should resist the maximum shear stress in this plane, and this nail should resist the maximum shear force in this nail, right? So then what will be the consideration of Q? So that will be, see, we need to find out this plane ka shear force and this plane ka shear force. So we can calculate, we can take this value, this area for Q, and we can say that Q is equals to VQ divided by I. But here the Q is in this region and in this region. So this is Q total, and here it is Q each. Here it is Q each. From symmetry we can say that both are same, right? So Q total, so Q each will be is equals to Q total by 2. Similarly, if you take here, you will take this area. So here Q total will be is equals to VQ by I, and Q each will be is equals to Q total divided by 3. That can be, these Q's will be same because of the symmetry, or you can say from moment equilibrium we can say also that one. But see, if you see this, sometimes it will be confusing to find out the area to be considered for calculating Q. So let us have some method, easy method to find out the area for consideration for calculating Q. See, if you take this one, first you need to find out the neutral axis. Okay, I find out the neutral axis, found out the neutral axis. This is the neutral axis for this cross section, and fix the structure below the neutral axis. So I will fix this structure below the neutral axis. Okay, I fixed, and push it. So you will trying to push it. Okay, then see if these bolts were not there. So this one and this one will get shear off, right? So observe which part is about to shear off and consider that area for Q. So this part is going to shear off from this one, right? So from this one, this part is going to shear off. So consider this value for Q. So Q total will be is equals to VQ by I, right? So Q total here, see here two bolts and these are symmetrical from this axis. So we can say that will be 2Q each. Okay, understood? So this is a simpler way to find out the area for considering for calculating Q. So if you see these parts again, so if you fix this one and push that, then we can say that this will shear off. So we should consider this one. For this case, if we consider this as fixed one, so if you push this one, so this area will get shear off. So we should consider this one. And for this, if we fix this one and push that, so this area will get shear off. So we should consider this area for calculating Q. But here three bolts that are symmetrically placed. So Q total will be equals to 3Q each. Here Q total will be equals to 2Q each. Here Q total will be equals to Q each. That will be equals to Q. Okay. I hope you understood this concept clearly. If you like this lecture, please subscribe to our channel 9pointer. Thank you.